We've all been sold a massive illusion. We call it the cloud, this borderless, weightless digital realm where everything just magically happens. But behind every single AI prompt you type, there's a heavy, industrial, and intensely thirsty physical cost. Artificial intelligence feels invisible, doesn't it? It feels like pure software. But behind every generated answer, behind every digital action, there is dense physical hardware. And that hardware produces an intense amount of radiating heat that requires absolutely massive infrastructure just to keep it from melting down.
Let's uncover this hidden physical cost.
As global AI workloads explode right now, the conversation has to go way beyond just writing better code. In this explainer, we're really talking about heavy industrial engineering. The physical reality of a data center is the exact opposite of a weightless cloud. It's incredibly hot, and it relies on extremely complex cooling systems and staggering amounts of water.
To put that scale into perspective, 5 million gallons. A single large data center can gulp down up to 5 million gallons of water in just one day. That is literally the daily water usage of an entire town of 50,000 people. And as AI keeps advancing, that thirst is only going up. Let's break down the invisible heat system that makes this happen. To really comprehend why AI is so thirsty, we have to look at the nuts and bolts. AI runs on densely packed graphic processing units, or GPUs. When electricity flows through thousands of these chips, they generate extreme heat. To stop a total system meltdown, data centers rely on chilled water loops, towering evaporative coolers, and massive municipal water pipelines. It's a hardcore industrial process, completely hidden away behind warehouse walls. But here's the catch. The water use isn't just happening inside the data center itself. We also have to account for indirect water use. This is the water consumed miles away by the power plants that are actually generating the data center's electricity. Think about it. Roughly 56% of the U.S. electrical grid powering these giant facilities still relies on fossil fuels like coal and natural gas. And those power plants are essentially just giant steam engines. They superheat massive boilers of water to produce steam, spinning the turbines that ultimately power your AI prompt. So how does AI infrastructure actually chill out? Well, the process generally follows a standard evaporative cooling loop. Step 1, the servers generate heat from electricity. Step 2, chillers and internal water loops absorb that heat. And step 3, that warm water is pumped out to massive cooling towers, where some of it is evaporated right into the atmosphere to reject the heat outdoors. It's highly effective, but man, is it water intensive. It's a lot like how traditional flood irrigation in farming wastes vastly more water than targeted drip irrigation. To manage all this, engineers use an industry-standard metric called water usage effectiveness, or WUE. It basically tracks exactly how many liters of water are consumed for every single kilowatt hour of IT energy used. It's the primary way operators measure and try to optimize their water efficiency. Currently, the industry average sits at about 1.9 liters of water consumed for every kilowatt hour of energy. That gives us a baseline, but honestly, in a lot of regions, it is far higher than it should be. Now, a WSE of 0 is technically possible, but it's incredibly difficult to pull off without dramatically increasing the amount of electricity you'd need to run traditional mechanical air conditioning instead. And that brings us to the core engineering dilemma. It's a strict, uncompromising physical trade-off. If you want to save water by using standard mechanical air conditioning, you have to use significantly more electricity. But if you want to save electricity and lower your carbon emissions, evaporative water cooling is vastly more efficient. So if you're the systems engineer, which resource do you choose to strain? The power grid or the water supply? This dilemma directly impacts local communities under stress. Because this choice isn't just some abstract engineering puzzle. While AI is a global borderless technology, water stress is intensely local. When data centers get built in dry, drought-prone regions, those millions of gallons they withdraw every day create real, tangible planning conflicts. Local communities are literally forced to balance the economic promise of new digital infrastructure against the preservation of their vital, limited freshwater. So what happens next? Let's look at the future of cooling. The industry definitely isn't standing still. As the power density of modern AI chips scales up, moving from 200 watts to 400 watts and beyond, traditional air simply cannot move the heat fast enough. The laws of thermodynamics are physically forcing the tech industry to abandon air cooling in favor of highly efficient liquid cooling. There are some really fascinating engineering advancements defining this next generation.
We're seeing a shift to direct-to-chip liquid cooling, which acts a lot like precision drip irrigation, but for silicon. We're seeing closed-loop systems that actually recycle the same fluid over and over without evaporating it. Some facilities are even taking entire servers and fully submerging them in non-conductive synthetic fluids. Add to that the strategy of smarter geographic siting and using recycled non-potable water, and you start to see a realistic pathway to true efficiency.
Ultimately, it all comes down to the physical reality of AI.
When we step back and look at this system as a whole, the main takeaway is that AI is not magic. It is machinery. The future of artificial intelligence isn't just about training smarter software models. It's strictly bound by the physical systems that make it possible: the power grid, the cooling mechanics, the water flowing through the pipes, and geography. So as we continue to build this invisible intelligence, we have to ask ourselves, are we fully prepared for the heavy physical cost of our digital future?